Welcome to Build on Balancer, where today we will explore an example contract that uses a custom router, NFTs, and hooks to manage users' liquidity positions. But first, a huge shout out to John Grant, the big brain behind the example contract we're about to walk through. Highly recommend checking out the link to his article which inspired this video. Let's begin with a broad overview of the role each component plays in the example contract. A specialized router enables the implementation of custom logic for add and remove operations. NFTs are used to keep track of metadata about the user's liquidity positions, including the timestamp for when they added liquidity, and a hook calculates and charges the fee taken from the user's position when they remove liquidity. Looking at the contract's definition, we can see that these three building blocks are directly inherited, but instead of reading this contract top-down, let's step through the execution flow for add and remove operations, starting with a user who wants to add liquidity by calling add liquidity proportional on the example contract, which is a function that accepts important arguments like the address of the pool, the max token amounts in, and the exact BPT amount out. And it passes these arguments along to underscore add liquidity proportional, which is where the custom routing logic begins. Let's pull up the standard router for comparison. Notice that the minimal router deviates by extending the add liquidity hook params to include a receiver field, which allows for the minting of BPT to the NFT LP example contract instead of the user. But first, let's focus on understanding the pattern a router must use to interact with the vault, which starts with calling the unlock function, with a bytes argument that is actually an encoded function call that the vault will use to call back at the message.sender. So in this case, we're telling the vault to call the minimal router's add liquidity hook function with the extended param struct as the argument. From there, the router is allowed to call the vault's add liquidity function with the extended params.receiver address as the value for the to field, which is how we are able to mint BPT to the NFT LP example contract. Now, you might be wondering, what is the purpose of this on before add liquidity hook? Well, we want to prevent other routers from being able to add liquidity to pools that register using this hook, which we can do by adding this only self router modifier, which calls ensure self router to block the transaction if the router address that initiated the add liquidity call on the vault is not the address of this contract. That way, we can ensure all users who join this pool are subject to the decaying exit fee that will eventually be charged during the remove operation. But first, let's finish off the add liquidity execution flow by examining the NFT that is minted to the user, which keeps track of the BPT amount out, the timestamp of the block, and the pool address by associating each add liquidity operation with a unique token ID. So to recap, the NFT LP example contract custodies all of the BPT on behalf of the users, who instead have their positions represented by NFTs. Now let's move on to the main attraction, removing liquidity, which is where the decaying exit fee is calculated and applied via the on-after remove liquidity hook. But let's start from the beginning of the execution flow, which is triggered by a user calling remove liquidity proportional with the token ID of the NFT they own as an argument, which allows us to read the state of this contract to grab the pool address and BPT amount associated with the user's liquidity position. Additionally, be sure to notice this ABI encoding of the token ID that is passed along as bytes memory user data. This is how we are going to access the timestamp of when the user added liquidity from within the on-after remove liquidity hook, but more on that in a minute. First, let's review the process routers must follow to interact with the vault, which must begin with invoking unlock using an encoded function call that specifies the function that the vault will invoke on the router. In this case, we're having the vault call the minimal router's remove liquidity hook with extended params that include a receiver address. That way, we can have the vault send the tokens out to the user even though they're not holding any BPT. But before that can happen, The remove liquidity hook in the minimal router will need to call remove liquidity on the vault, which triggers the vault doing some accounting to compute the proportional token amounts out before it moves on to invoking the on after remove liquidity hook, which is where the decaying exit fee is implemented by adjusting the token amounts out that the user receives via this return value. Let's step through the logic, which starts with decoding the token ID from the user data, which remember was originally encoded during the remove liquidity proportional call to this router. Next, the hook adjusted amounts out is initially set to the amounts out that the vault calculated, and then the fee percentage is computed by calculating the number of days that have passed since the user added liquidity and decrementing the fee by 1% per day pass. If the fee percentage is greater than 0, the hook adjusted amounts out are altered by a take fee function that declares an accrued fees array to store the amount subtracted from each token by this for loop that calculates the exit fee amount, updates the accrued fees, and reduces the amount of each token the user receives. Then the take fee function finishes by calling vault.addLiquidity with the amounts in set to the value of the accrued fees and the kind set to donation so that no BPTs are minted, which effectively means that the full amount of the exit fee taken is distributed to the remaining diamond-handed liquidity providers. After that, the execution flow naturally returns to the remove liquidity proportional function, which finishes by burning the associated NFT. We hope you have enjoyed this example that demonstrates how custom hooks and routers can be combined in powerful and flexible ways on Balancer v3.